Очень красиво. Very beautiful formula. A certain differential operator acts on sure function, and this was an eigen problem. And this was related to it was a reformulation of cut and join equation. Cut and join equation describes how to say the result of как сказать слияние слияние двух точек ветвления, a result of concatenation, yes, of two branch points. The first version of this equation was written by Guldon and Jackson. It was about double. Черт, я не ожидал, что по-английски придется говорить. It was about double branch point with Young diagram, which 2, 1, 1, 1, 1. And there was an equation written by Guldon and Jackson in terms of high times in terms of high times of Kadamtsev-Petriashvili integrable equation, Kadamtsev-Petriashvili equation. It was certain differential operator of second order, which act on a polynomial in high times, which was indexed by partition, and it gives another polynomial indexed by different partition. And this is about how what branch point, like you see, we have Young diagram which describe ramification ramification profile is just 1, 1, 1, 1, and in one place it is 2. It is this. These are leaves of Riemann surface. And when we go closer, we get another ramification profile, and this was equation written by Guldon and Jackson. Mironov-Morozov-Natanzon consider more general situation when just two arbitrary ramification problems go to one another, and the result is described by equations they written down. And this equation actually is nothing but in certain variables but Calogero-Moser, quantum Calogero-Moser equation in simple point for simple value of coupling constant, where Jack polynomial, which is eigenfunction of Calogero Hamiltonian, start to be sure function. What for this very Calogero system actually is equivalent somehow, it is quite unexpectedly equivalent to to the generalized cut and join equation. And I will speak about generalizations of this Mironov-Morozov-Natanzon cut and join equation.
Sasha, I'm sorry, before your slides was ready, could you give more details about the context of this subject? So you compare the quantum Hamiltonian system, the classical ones, maybe some other. So what is the domain of mathematical physics your works?
I should say it is a little bit, how to say, it is a little bit separate. I hope it will be a part of quantum integrable systems, because I will write down some commuting differential operators where variables, commuting it is differential operators, and variables are just entries of certain matrix. And maybe not one matrix, but ensemble of matrices, ensemble. And hint.
I'm sorry. Could you give a geometric interpretation of these variables? Does they somehow related with the embedded graphs?
Yes, it will be related to embedded graphs as follows. We consider some orientable Riemann surface, but we will not. We are not interested in complex structure, just topologically. We have some Riemann surface and embedded graph. Embedded graph means that each face of this graph is homeomorphic to disk. No, I consider it to be polygons in my talk. It is not in, how to say, polygons because it has edges in this up to homeomorphisms. And to each edge, I relate a random matrix, complex random matrix. And we have some, what does it mean random? Each entry, perhaps I got, спасибо большое. Each entry has a distribution, Gauss distribution. And each entry is independently. It is called actually, and they form, these are entries of complex, a complex matrix. Yes, no, we will have ensemble of matrices, but сейчас я.
What the dimension of the matrix?
N by n. N should be large enough. I will consider partitions, and the dimension should be should exceed the weight of partitions.
If you write something, we don't see it.
Repeat, please.
If you write anything, we don't see it. We see only you.
Yes, I got this file. I got the file. Short. One moment. Черт, он... Я не понимаю, почему он повернут. Мне его сейчас разворачивали. Провалить пропадом.
Саша, покажите свой рабочий стол, может, мы разберемся вместе.
Черт побрал.
Демонстрацию экрана включайте, может быть, мы сейчас найдем.
Сейчас. Я дико извиняюсь, конечно.
Не беспокойтесь, сейчас найдем решение.
Очень нехорошо получается. Сейчас. Сейчас вот share screen, yes? Share screen. Share screen. И вот этот вот текст.
Лучше везде, чтобы продемонстрировать, чтобы мы разбирались, чтобы мы видели именно то, что вы видите.
Ну вот он виден вам, текст?
И пока ничего не видно.
Он, зараза, повернут. Провались пропадом. Этого я не понимаю.
То есть вы нажимаете на зеленую кнопку, потом появляется список типа документов. Самый первый будет экран, весь экран. Вот.
Хорошо.
Надя, он все равно повернут.
Почему?
Черт его знает.
Подожди, а ты не то, это самое открываешь. Ты старый открываешь вариант, открой новый.
Да. Ага, сейчас я извиняюсь. Ага, сейчас. Черт. Вот это, да? Ага, сейчас.
Так, подожди, ты что-то не то вообще
Нет,
смотришь.
вот оно. Вот оно, вот. Ярославль 2, да?
Да, вот Ярослав 1, 5, 6, 9 и 10, 13.
А, по отдельности будет, да?
Да.
Угу. Хорошо. Спасибо. Спасибо.
Не за что.
Во. Ура, видно?
Нет.
Нет, не видно.
Не видно? Сейчас.
А, может быть, у вас два экрана?
Сейчас, черт его знает. Сейчас, минуточку.
Что?
Сейчас, мне нужно в зум. Где тут этот проклятый зум? А, вот он.
Вот он зум.
Вот тут? Вот тут?
Нет.
Нет.
Вот он зум. Ну,
Нет.
тыкай. А
Мне
что
нужно
зум?
тыкать зеленую раму. Вот эту мне
Вот
скорее
сюда.
нужно. Вот так?
Вот сюда тебе нужно тыкнуть. Нет,
Ну, чтобы он расширился.
не знаю.
Зараза. Сейчас.
Так, подожди. Вот это вот надо закрыть.
Может быть, старт?
Нет, старт видео тебе точно не надо. Вот это тебе надо закрыть просто.
Вот это, да?
Да,
Я
вниз-
закрыл уже.
Вниз сюда.
Сейчас вот сюда, да?
Нет, вот видишь,
Вот
стрелочка,
сюда?
стрелочка
Ага,
вниз.
сюда. Ага.
Так,
Итак, теперь
вот,
share screen, да?
так.
Share screen и вот
И
это вот.
вот
Ярослав.
этот.
Вот так видно?
Да, очень
О.
хорошо.
Ой, ну все, спасибо большое. Ага, все, спасибо большое. Вот. In English. Черт. Сейчас, а как это убрать? Вот это. Вот это вот.
Не знаю.
Чё,
Вот
не
на
мешается?
минус нажми.
На чат можно нажать.
Слева можно выбрать слайды
Да,
отдельно.
все, вот.
Слева.
Так слышно и так видно, что я
Да, слышно, видно.
экран виден, да? Ну, I will speak in English. Let us consider Riemann sphere, which consists of two disks. What these two disks, P1 and P2. And equator will be our graph, equator with a point with this vertex O. What this is, equator. So we have two disks, and we consider Riemann sphere as glued from two disks. Okay? Ага, до свидания. Спасибо большое. And now consider the first part of my talk will be this related to these random matrices, how to get certain relations with the help of them. Okay, so consider coverings with 3 branch points. Our branch points will be our vertex O and 2 chosen points inside both disks, say south and northern poles. We call it capitals of our faces. So we have 2 faces, graph with 2 faces, and there are capitals. And O1 and O2 will be 3 branch points. So how it look like? I just people know this. It of course but consider for instance pre-images of our vertex O. We have, you see, we have what these are pre-images. Here we have 2 half edges which go out of our vertex. And pre-images, for instance, this is example of pre-image. This we have 3 pairs. We have here 1 pair, here 3 pairs. It means that locally our map is Z cube. What for this picture we have 3 numbers, 3, 3, and 1. And this 3, 3, and 1, it is called ramification profile of this branch point. And this is partition. So partition for ramification profiles. And for these capitals O1 and O2, we also have some ramification profiles. I call it mu upper 1, mu upper 2. No, this example of, for example, 3, 2, 2. And so what does mean? We have, actually here we have one gon on the base. This is base surface, this is covering surface. So on the base we have one gon with this one edge. And here it will be 2 gon, and 3 gon. So 3, 2, 2 will be our partition, our ramification profile. Now I start to try to very quickly to explain this. So on the covering surface, we have what in this case, two gons, 1, 3 gon, 4 points, say, or 1, and some other polygons for other points. And now let us denote the number of ways in how many ways we can glue these polygons on the covering surface to get surface. It may be disjoint. So the preimages of our one gons we should glue, and we should glue in a way. What, look, I specially made it dark, no, black, say black, this disk, and this white. And our edge divide black and white. And the same will be for our preimages. So when we glue polygons, we should glue them in this way that each preimage of each edge divide black and white polygons. So denote this number n, and we introduce equivalence of the gluing. We can, if we have polygons with the same number of edges, we can permute them, and we can rotate polygons. And we do not want to count these things, so we divide what this number of ways to glue to this automorphism. And this automorphism are, how to say, very well-known numbers. If we have partition with M1 paths equal to 1, but this M2 paths equal to 2, and so on, with this number, some people call it automorphism of Young diagram. I think it is not very good. Just what if we have equal number in Young diagram, which is related to the partition, we can the factorial of ways to interchange them, and then what this k we can rotate it. It is if the length of the row is k, so we can k rotations. So, and this is called, what this ratio is called Hurwitz number. It is a number of non-equivalent covering with given profiles, ramification profiles. No, when we glue polygons, we get something in the vertex. Some partitions in vertices. Okay. Let us no, and more generally in certain Riemann surface omega, we have embedded graph So all faces are polygons, and so this is on the base. Then we consider coverings, and in each polygon we choose some capital of polygon and say that we want to have ramification profiles given by this set of Young diagrams. For P1, for polygon P1, it will be mu1 and so on. We have F, say F polygons, we have M profiles in the capitals of these polygons. Now, say we consider Riemann surface omega with F faces and edges and V vertices. Okay. So, and if we have, say, if P1, for instance, is triangle, yes, then this ramification profile means that in the covering we have two six-gons, шестиугольники, and one triangle. You see, because no, clear, yes, this is, we have
Yes, it's okay.
clear. Okay. Shoot. And the same. What we have a number of gluings. We have some automorphism, rotation of polygons and permutation of polygons, and so this ratio is called, may be called, it is geometric, one of the definition of Hurwitz number. Okay, and for Hurwitz number, the following formula is famous. It is, people call it Frobenius formula, Bernstein formula. Actually, in Frobenius was the simplest version of it. And I don't know who was the first, perhaps Bernstein. The formula for Hurwitz number. If we have a set of profiles, what these are set of partitions, and partitions of the same weight, and the weight of partitions is the number of preimages in general point. Если количество листов в общей точке, они сливаются в точке ветвления, а в общей точке, and the weight of all partitions are equal and equal to this number of preimages in general point. And yes, and the formula for Hurwitz number is the following. It is sum over partitions, lambda, of the same weight, with certain multiplier. I will not explain. I'm afraid I have no time. And times product of characters of symmetric group Sn and n equal to the weight of all partitions involved here. Notice some normalized characters, not exactly characters related to this representation evaluated on this cycle. What is written here. So this is formula. Actually, the same formula, what here we have Euler characteristic, and the same formula for non-orientable surfaces and coverings was obtained by Alexander Mednych in Novosibirsk, in 60s. So this formula is also true for non-orientable surfaces. Okay. Now we had a graph. Yes. Hello? Что?
The formula you just showed, the phi's I should view as a character on a conjugacy class. Is that it?
Yes, exactly. Oh, and mu, what this? Yeah.
Mu is your conjugacy class.
Yeah, this is a cycle structure.
Yeah.
Of this class.
Thank you.
And this is a representation. No, it is not exactly character, but divided on somewhat actually. No, okay. No, not important. Now, now consider again our graph on Riemann sphere. Now we inflate our vertex. We have, I say, one vertex, we had one vertex, one edge, and two faces. And now we inflate the vertex. And we assign, yeah, okay. And to the edge, we assign two matrices, Z and Hermitian conjugated from the both sides of this edge. Actually, perhaps I should, okay. And when we go around the boundary, our face inside our face around boundary in positive direction, what this is positive for it is include infinity, so this is positive. We have Z and then C1, and we call it monodromy of this face. So product of Z, what we go around, so first Z, then C1, and this will be monodromy. What? This is Z, C1, monodromy of polygon number 2. What this is polygon number 1, gon number 2. And and for this, what duck, we have monodromy also in a positive direction. We have that Hermitian conjugated and then C minus 1. This will be monodromy of the other polygon. Then let us remark, sorry, excuse, we can, to each entry, we assign an arrow. What entry ij, entry with two numbers in the beginning and in the end. But we have two sort of matrices, because later this will be random matrices, and this will be some, how to say, source matrices, constant matrices. So this will be solid, each entry solid arrow, and this punctured arrow. And what is product of matrices? We have just consequent arrows. Yes, because in product we have the beginning and the end of entry is the same. So the product of matrices will be a chain of arrows, and the trace of a product will be closed chain. Is it clear? Yes? Is it clear?
Sasha, yes, principally it's clear.
Okay.
Yes, it's okay.
So we have what we have these monodromies, and we have these traces, and these traces is just a no, here it is only two arrows. What we have punctured arrow, here punctured arrow and then solid arrow, and here also punctured and then solid. Okay. Now consider what this Z to be random matrix. It means that each entry is distributed. No, let us distribute it according to this law, to Gauss law. Yes, independently. Each entry is independent. And for the whole matrix, we have many entries. We have this measure. Yes, with this probability measure, and the average of any function of entries is given by this formula. Now here some normalization constant, and one can calculate that these pairways. What if f means if is this product, we have what this. So non-zero, we obtain non-zero only when beginning of this arrow coincide with the end of this arrow, and opposite. Okay, and we have weak rule that this is Gauss integral, that this is actually a product of pairwise correlator. Perhaps I
Sasha,
will
am I
not.
right that the measure should depend on z plus, on zeta plus?
No. No, I do not think.
Okay, it's a little bit strange.
It is how to say. Just I cannot use the word.
Okay. That is a conjugated. Okay.
Yeah. It is how to say. Maybe not Gauss but people call it Gauss. It is not Gauss.
I'm sorry. It's okay. It's my mistake. Sorry.
Yeah. And actually, this is called Genibr ensemble, complex Genibr ensemble. What ensemble of the random complex matrices, complex Genibr ensemble. In physics, it appeared in physics to describe quantum house with decay. If it will be Hermitian matrix, it will be, how to say, it will be famous Wigner ensemble or orthogonal or quaternionic, but this is complex, and actually it is rather popular in information theory. How to say, передача информации, в теории передачи информации and in quantum house, this Genibr ensemble. Okay. Now, it is actually, just one moment. From what I said before, it may be actually concluded that that this average of, you see, this is, I should say the following. On the covering, you see, on the base, we consider trace of this and said that it is some polygon, some polygon with one punctured arrow, one solid arrow, with numbers in the ends of arrows. And on the covering, we have how to say, расширенные полигоны. We have not extended. One gon, but mu1 gon, mu2 gon, and so on. And this present these polygons. And Wick rule gives us the following. We should glue these arrows, and gluing of these arrows, it is exactly a way to glue polygons on the covering surface. To glue polygons. So this average, what this is automorphism factor, and this average, we have, these are preimages of one polygon, these are preimages of other second polygon, and as a result we have this sum. We have maybe it is better to explain why we have here each time this product. No, actually it is, how to say, geometrically it can be seen. You see, maybe I will not, I don't know, maybe I will not not look, what, trace, yes? We have this, and we glue it. Черт, тут плохо, я не нарисовал. No, okay, we glue what these polygons, what these dotted, punctured arrows, and we get these polygons, how to say, structure, a graph on the covering surface, and exactly as we get So we have a definition that number of ways to glue polygons on the covering surface, which result in this ramification problem in the preimage of vertex. These are Hurwitz. This is Hurwitz number related to this three profile. Maybe it is too quick here, but perhaps better just to write more carefully, but better to believe. Okay, so we have this formula, Frobenius formula, with these characters. Yes. Yeah. I want to say that this is very important for us. What this equality will be central for us. No, it will be the main example. I will use the following notation. But traces of certain matrix will be denoted by this P. It is Newton sums of eigenfunctions, but in our case, later it will be differential operators. So better not to speak about eigenfunctions. Just we have trace of power of a matrix, and this is called Newton sums or power sums, a set of variables very well known, of great use in symmetric functions. And we have the relations between these variables and sure functions. Well, this is so-called characteristic map equation. Here it will the same what normalized characters as we have in Frobenius formula. No, this is some rational number. It is dimensional representation, and this is just a size of permutation group, number of elements in permutation group. So these variables, sure functions, are related to these variables. So these variables are explicitly written, so one may consider it as definition of sure function. Okay, what? Sure function evaluated, no, actually sure function is a character evaluated on some matrix, what Z linear group, yes, and we have what, and there is this relation. Here are traces of Z in certain powers, and these powers form partition. And we have summation over this partition mu. And this is characters in representation lambda evaluated on these cycles mu1 and so on, mu2. Oops. Now, sorry, let me take 1 minute to take another PDF file. 1 minute, please. I'm sorry.
Yes, surely.
Сейчас, черт, сейчас. Ах, черт, это не тут. Так. Так, я вывел на экран. Сейчас мне нужно это... Сейчас мне это нужно... Сейчас. Черт. Сейчас, минуточку. Черт. Этого файла не видно?
Пока нет.
Так. Вот так. Потом. Так, это я закрываю. Сейчас. Где я? Сейчас, а почему он мне показывает? USB-диск мне нужен, наверное. Да? Да. Вот он, вот. Сейчас видно?
Видно только экран.
Сейчас я сделаю.
Файл не видно.
Сейчас сделаю. Черт. Сейчас. 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 Почему-то я не нахожу. У меня компьютер, что ли, глючит? Черт.
Уже надо стоп-шеринг сделать. Потом найти шеринг снова и найти окошко, в котором файл открыт.
Саш, я не могу, главное, найти эту рамочку с зумом. Черт, она почему-то... Вот так, может быть, откроется. Не открывается, зараза. Вот. Ты открылся. Тебя вижу. Вот так. Сейчас.
Так получше?
Что нужно сделать? Вот. Вот так. Вот так. И вот так. Видно?
Нет. Нет.
Видно?
Нет.
Черт. Что я должен сделать? Что-то я...
Ну, просто переключиться в другое приложение. Оно вот где-то мелькало сейчас. Сейчас, Саша, сейчас ты водил мышкой.
Сейчас вот...
Где-то он открыт.
У вас один экран или два экрана?
Тут непонятно. Сейчас.
Давай я еще раз остановлю трансляцию.
Черт. Сейчас я снова попытаюсь. Так, USB-диск. Я тут вывожу вот этот текст.
Надо открыть окно, в котором ты видишь файл. Ты открыл файл свой?
Да, вот я открыл файл.
Вот, теперь, значит, когда зашел в шеринг, находишь окошко, где открыт этот файл, и его, так сказать, шеришь.
Шеринг. Вроде бы я так и делал. Вот я так делал. И так делал. Черт. Так, видно что-нибудь?
Нет, нет.
Нет, не видно. Я думаю, что проблема в том, что открывается у вас в другом экране. У вас один экран.
Да я вот не знаю. Но я вижу один экран.
Но дисплей один или
Я, к сожалению, дурак. Вот не знаю. Сейчас я... Черт, почему же раньше открывалось? Я не понимаю. Ну вот, я делаю share screen. Там я вижу окошко, вот там у меня флешка.
Тогда давайте, там в списке будет и сам файл, который вы открыли, там PDF, который Ярослав...
Вот я открываю тут вот
да,
USB.
выбирайте файл.
У меня на флешке, вот, и я его открываю. Может быть, стоп-шер нужно сделать, а потом снова...
Да, но попробуйте стоп-шеринг.
Ты его видел на экране. Ты видишь файл?
Да, сейчас.
Открой
так,
его
сейчас я
на экране.
Снова попробую провалить.
Ты открой файл.
Вот так вот.
Ты его видел.
Вот так.
Ты видишь свой файл?
Открытый.
Я вижу. Открылся?
Ты читать его можешь? Ты видишь картинку?
Я читать могу.
То есть файл у тебя открыт. Ты его хочешь показать.
Да.
Когда переходишь в share, находишь, где он открыт. Не флешку, где он находится, а где он открыт.
Да, вот. Но уже, до этого же я открыл. Черт возьми, а.
Вот отлично.
Сейчас нормально.
Супер, супер.
Вышло?
Да, Саш, продолжаем. Ага.
Фу ты, но я же то же самое делал до этого, я не понимаю. Ну ладно. Вот. Теперь, значит, если мы... Вот те формулы, которые я писал, там были только вот тут вот одни трейсы. Sorry. There were only traces in this. And now, using Frobenius formula and orthogonality of characters, what this, orthogonality of this, we can, and do you remember this characteristic map relation which related these traces to Schur functions? We can, instead of traces here, to write here Schur function and rewrite it in this form. Look, rewrite in this form. Great. Then we can do the following thing. Do remember weak rule? Weak rule, it is pairing of each z DAG with z. And we can, in case of weight of this partition and of this partition, and they are of the same weight from the very beginning, we can just, instead of pairing, we can interpret it as the action of differential operators on entries. Like we, for oscillator, instead of creation elimination, we have derivative, say, x and ddx. But important that it is for the same weight of this mu and this lambda. And then if we rewrite it, we write it as this differential. What this will be differential operators. So instead of that DAG, we use a matrix of derivatives. Matrix of derivatives. What this matrix, but transposed. What this matrix of derivatives. And so we have this but I wrote it for some special case. I wrote it for a special case. Do you see here this constant? This constant, it is not random, but just a source matrix, C minus 1. And let us take it equal to Z. It is forbidden here. We cannot pair. We have all pairings already. But in this presentation with differential operator, we can put here dots. It is normal ordering. It means that all differential operators here, which is here, does not act on coefficients of these operators, which depend on Z. And this operator, we denote this, and it is more or less known operator in actually. Okay, I will not speak. So what this D, it is good object. So we have here inside of P, we have D times, how we rescale this C1. Instead of C1, we consider Z times C1. C1 is constant matrix. This Z is matrix Z, But now these dots means that this differential apparatus does not act on the coefficients of this operator. And we have this equality. Look, we have this equality. Now, if we consider all this C equal to 1, but both this C minus 1 and this C, then we have eigenvalue problem. We have Schur function on Z, evaluated on Z, matrix Z, it is character of linear, this group element Z, trillion, C, and here we have this. And here we have some eigenvalue. You see? Now here I repeat, important that the weight of this partition is equal to the weight of this partition. Okay? And yeah, what I spoke, this is what about this. So we have this equality, this normal ordered operator, and this is exactly generalized cut and join equation found by Mironov-Morozov-Natanzon, who found first generalized cut and join equation in variables of classical integrable systems from vertex operator of Kazimir-Petriashvili equation, but then rewrite it in other variables, in so-called MIVA variables used in soliton theory, and rewritten in MIVA variables, it is this, exactly this equation.
Such could be considered as an analog of the Capelli identity.
No, here no. What all my examples will not have anything to do with Capelli. But Capelli is somewhere here. I mean, if we consider different what these matrices see, but it is different topic. Okay, the interesting thing, I don't know, is it written, was it written in Mironov-Morozov-Natanzon work? Perhaps not, but the fact it is no. It is actually, it is so-called Laplace-Beltrami operator. And if it acts on symmetric function of matrix Z, then its radial part is exactly Calogero Hamiltonian. No, up to some сопряженный там с помощью Вандермондов. Но yes, it is Hamiltonian of the quantum Calogero, but in special point. What in point when Jack polynomial is Schur polynomial.
But quantum Calogero, in which situation? For what are the parameters? How many particles? The spin version.
Eigenvalues of this matrix are coordinates of particles, but perhaps not exactly Calogero model, but maybe Rudgenars, maybe. Ну, тот Calogero, в котором экспоненты от координат частиц вовлечены.
It's probably related to the Rudgenar system.
Yeah. Yes. But it can be considered as just differential equation in other variables, in entries, because this is polynomial in entries. What Schur function is polynomials in entries of matrix. This is polynomial also in entries and in differential operator in entries. So our variables are entries of matrix Z, but in case of when this constant matrix are just, remember we have C1, C minus 1, or C minus 1 and C. No, here we have, I said, we made this replacement, and after that call it C minus 1. Okay. Okay. So, and in the paper of Mironov-Morozov-Natanzon, it was, how to say, it was approached from quite different direction to this cut and join equation. And in this approach, I said, it has this meaning. We have two polygons. One polygon is related to differential operator, the other to a matrix, and we have this Hurwitz. The result, this is, as I said, it is a gluing of two polynomials. In this interpretation, it is gluing not sides of edges, but half edges. We should consider dual graph, and the half edges. So this, how to say, describe gluing of half edges. It is just what differential operator act on what here, what differential. Yeah. Important that in this situation, actually, we can omit the request that weight of mu is equal to weight of lambda, because we can complete this cycle. Perhaps I will not stop on it, but it is important moment, but I will not explain it. The weight of this mu, if the weight of mu exceed the weight of lambda, it is just 0, because here we have more differential operators than here variables. But if it is smaller, it stays to be correct with some correction to this eigenvalue. We should so-called, it is a topic of completed cycle. We should complete the cycle mu. It is smaller, but we complete it by one box, by a leg. Unit diagram consists with one box. It is possible to do here, but I don't know how it is possible to do in other cases. I will consider. I want now the first generalization with one matrix. What we have, as I said, what this simple graph, only one edge and one matrix, random matrix, and the generalization is the following. If we consider here not this Laplace-Beltrami operator, what this, which commute actually. No, I do not want to go to this topic. It is a center of enveloping algebra for GLN. So this is, how to say, familiar operator. And if we add here some constant matrix, it is not the case. Yes, and here, of course, they commute with different mu. All these operators with different mu of different sizes, they commute. And now consider what the first, from this graph consideration with matrices, the first generalization. Let us consider, yes, but consider here A. Let us add here A. The action on Schur function of such operator will be, we have not the same argument, but shift Z by A. Shift. But
Sash, could you explain more precisely the simple case without A, just with the...
What is this? This case. Yes, this?
Yes.
This case.
Yes.
Here, no, first of all, I want to say that we have add here any constant matrix what here. If we just make a shift of Z, there will be no shift here. And so if we, not only this is correct, but also with matrix X, or with some matrix C is correct. So, Dima, and what to explain more about this
I just don't understand what is P mu of D.
P mu. It was extremely sorry. But P mu, if P mu of some matrix, this is matrix of derivative. But this D, if you remember, it is just a matrix whose entries are some derivatives.
Partial
Not
derivative with
just
okay.
what this. So each entry 1 1, it is, we take 1 1 here and sum. So the entry of this matrix 1 1, and we know what is trace, and we know what is the product, and take trace of this product. And we have a set of numbers, mu1, mu2, and so on. It is partition. It is partition. What is partition? So,
so for example, for mu equal 1 0 0 0, what is this?
For 1 0 0 0, it is just trace of this thing. It is matrix. You see. This is matrix D, what is written here, and this is matrix C. It is product of two matrices, and trace, it is just trace.
And what does it mean as an equation for the Schur function?
What some equation on Schur function? This I don't. It is good. It is a good question, but I yet do not. Perhaps you know. Perhaps you want to ask, if we go to eigenvalues of this matrix, will it be some analog of Calogero system? Yes. But this is a good question. Up to now I did not do it.
Maybe you know some other simple but non-trivial example of this construction, just to to understand better what is the measure of non-triviality of this result.
No, here we have, no, this is just an example, yes, and this is not eigenvalue problem. We have some, I want to say that all these operators are commuting, but we have a set of commuting operators in many variables, you see. This is good point. We have a set of commuting operators in many variables, and we have eigenfunction for this. We can consider some Hamiltonian or some quantum system, but it is written not in coordinates of particles as in Calogero, so in eigen value of z. Yes, but just in entries. You see, our variables are entries. You see, this is what we can consider it as some quantum Hamiltonians commuting. And here we have eigenvalue problem for it. But the point that this eigenvalue problem, so for any lambda, this, no, it is not written, sorry, what as it is written, it is not eigenvalue problem, but this is eigenvalue problem. You see, these are commuting operators, these are eigenfunction. We have commuting operators and eigenfunction. And this is polynomial in, for any lambda, what in this very case, just for any lambda, we have, it is eigenfunction of this operator for this set of commuting operator. But but new thing that you can consider more general situation because of these matrices we have. For instance, actually, I need one thing. I did not explain how we get this from graphs. Short. I didn't explain. I just say that it is an example, but did not explain how we get it. I should explain how we get what this sort of relation. Maybe a little bit later. I will explain it a little bit later. Okay, I will explain it. So we have here what I want to say, that this is another example of commuting operators and eigenfunction for it. See, this is another. I don't know what is how it may be called generalized, maybe Calogero system. Okay. This is another example with different graph. So we have, say, petals. We have the matrix related to each edge. We have this constant matrix in the corners of the faces. Yes, in the corners, this matrices here, we can write this, and we can write this. So instead of here it is, roughly speaking, product of, not roughly, but it is just product of Laplace-Beltrami operators, and this is eigenfunction. Now there are much more eigenfunctions for this operator. This is an example which follows from this graph, but I should explain how we write it. Maybe I later explain. Okay, later. So we have another system of here we have some generalization of this Calogero written. Okay, now let me take the last portion of so could I interrupt, take a few minutes?
Yes,
1 minute?
surely.
Mm-hmm. Черт. Так, сейчас я буду вводить диск. Буду выводить вот это. Черт. Это не то. Нет, не то. Сейчас, черт. Опять даже будет бодяга. Так. Так. Сейчас. Сейчас. Сейчас не видно?
Пока нет, пока нет.
Сейчас, секундочку. Так видно?
Нет, Саша, куда-то не туда опять жмешь, надо, видимо, вот жать на файл уже открытый. Надо его сначала открыть, и потом, когда ты...
Я его открыл. Ну ладно, сейчас я заново попробую все с самого
Мгм.
начала. Сейчас. Я не понимаю, что происходит. Ей-богу, не понимаю. Так, это я убираю старые файлы, все убираю, чтобы не мешались. Я, значит, сначала открываю этот диск. Вот он тут. Потом я открываю вот это. Потом я открываю вот это. Открылся? Нет?
Нет,
Сейчас.
нет.
Зараза. Блядь. Черт.
То есть алгоритм очень простой. Открываете файл, если вам видно, тогда снова делаете share screen, и там будет несколько окон на экране.
Я вроде
Выбирайте
так и делаю.
сам
Да.
файл, не самый первый, а сам файл.
Я вот так ровно и делаю. Вот сейчас видно?
Да, да.
Видно?
Да-да-да,
Да,
отлично.
видно, да.
Отлично.
Ну хорошо. Actually, I didn't explain how we write these relations for arbitrary graph. Let me explain the rule. Сейчас. How to... I didn't notice that maybe I just consider examples instead of general. First example. First of all, it is suitable to consider first of all, just I omitted this part. First of all, I should consider dual graphs. Dual graphs. Dual graph for my original graph, which was just one edge, one vertex, two faces. Dual to it is отрезок, interval, with one edge, two vertices, one face. And we have two disks, black and white, and here on dual graph we have two vertices, black and white. Black and white. And all examples for eigenvalues will be for bipartite graphs. Bipartite graph, these are graphs with black and white vertices, and each edge connect two different color vertices of different colors. Bipartite graph. Двудольный in Russian graph. Yeah, and what we do? So we have some bipartite graph with some black and some white vertices, and we assign monodromies to this to monodromy to white vertex and monodromy to black vertex. Dual graph, edges of dual graph cross one edge of original graph, and we put here on this edge of dual graph, we have two half edges. One belong to black face and the other belong to white. And so, and to white semi-edge of dual graph, we relate matrix Z, random matrix Z. We numbered all edges, no, and half edges, and to each edge we relate a matrix. All this will be different complex matrices, complex random matrices to each edge. Actually, to white half edge this matrix, to black half edge matrix of derivatives with respect to entries, no, transposed. Moreover, what here you see we have edge number one, this half edge will be assigned a derivative, yes, derivative. with respect to this matrix Z1, yes? And a rule, just we create to consider our eigen problem. It is just examples. It is not, it is just for our set of examples, the rule will be the following. To each semi-edge with number, say 1, we assign this, do you remember it was matrix C here? Instead of this constant matrix, we assign now matrix with the same number, Z. But we will not, we will consider differential operators normal ordered. So these operators, what this, of derivatives, will not act on the coefficients of which enter the monodromy of black vertex. The monodromy of black vertex will be the following. It is a product. First, what we go in positive direction around black vertex. Here we have edge, say number 1. Here we assign derivative with respect to matrix Z1. Then our rule, it is followed by Z1. Then we have edge number 2, and it will be followed by matrix Z2. It will be coefficients of our differential operators, but coefficients, на которые не будут действовать сами дифференциальные операторы. Знак нормального упорядочения нас, так сказать, освобождает от действия вот этих вот операторов на вот эти коэффициенты. Okay, so monodromy will be this product. So this derivative, then Z, then this, then Z2. You see? What? And in our notations, it will be this product of these two. No, in certain sense, Euler type operators. No, it is not Euler, but what monodromy, what in this, and in any examples, we have black vertex, and we have the same. We have just product of this D, what we go around and with semi edges, and we just consider product of this D. It is just an example. It is not, how to say, necessary for construction, but it is very suitable to have these examples. And monodromy, for it will be our differential operator related to graph. So it is a set of monodromies in each black vertex. We'll consider a set of monodromies. Then we consider trace of these monodromies. Then with the help of partition, we construct this guy, these power sums, which consist of traces of powers of this operator. Yes, I remember notations. Here it is not written, but do you remember this notation, power sum, labeled?
Yes. Please.
This is product of traces in power mu1, mu2, and so. So we have here we have some differential operator, and we have actually, if on graph we have a set of black vertices, we consider a product of these guys with different partitions mu1, mu2, and so on. What here in this example, what for this graph, we have one black vertex and we have, okay, monodromy our, okay, D1 and D2. What, D1, D2. Now I didn't say about white vertex. We have also here monodromies. Monodromies here will be just a product of these half edges. We assign, as I said, here matrix Z1, here matrix Z2, monodromy here Z1, Z2. What here monodromy is Z1, Z2, here monodromy is differential operator, and this act on this, what we get. And get the answer. The answer, because I did not explain it, the answer is a is a product of Schur functions with arguments which are monodromies of corner, monodromies of all face of, we should also introduce, we introduce here monodromies of the vertices. Let us introduce monodromies of faces. The monodromy of faces, what is the following? We go in positive direction and multiply all matrices. Here we have, I said, we assign after this half edge, we assign matrix Z1, and here we assign matrix after edge, semi H2. When we go this, we assign Z2. But Z1 belongs to this. It is a boundary of this face, and Z2 is boundary of this face. And here, in my example, you see, I consider all what matrices see here. I just choose for simplicity to be equal to 1. So we have no here, we have just identity matrices here and here. So our face monodromy will be just Z1 of this face. And of this face, it will be Z2. And we have the answer Z1, Z2, and some eigenvalue. Eigenvalue is as follows. Here we have this, and here it will be, I forgot, maybe it is minus or plus, I forgot, but actually it is a number of edges. Here we have two edges. But perhaps maybe it is minus, sorry.
No, Sasha, I'm a little bit confused. To which combinatorial data the operators are related? The operators Z, I, are they related to faces?
You see that that I is related to two objects, to white half edge, to white, Z1, Z2. And we just by hands, to construct our example by hands, we put here Z1 and Z2 because it is play the role of our C, this constant matrix C. I put it by hands, but I said at the same time that differential operator, which is related to this half edge and to this half edge, will not act on this very Z from black vertices.
Okay.
So because we need only matrix structure. So we need only matrix structure. It is not act, but matrix, it enters by matrix structure. Is it clear or not very clear?
Yes, it's okay. Please continue.
Actually, we have this face, and we have black vertices, and we have this arc, and this arc follows edge number 1. We assign here matrix Z1. If this arc follows matrix Z2, we assign here Z2 just by hands, because we have this freedom in the beginning in the constructions with integrals. We have this freedom. So we do it, and we get this operator, but with this normal ordering. Normal ordering means that in this operators D, differentiation does not act on the coefficients of this operator, but matrix structure is important. So this part is clear. So this is traces of monodromies of this differential operator to black vertex, and this will be eigenfunction. It is related to, it is polynomial in entries of these matrices. Here we have it is Schur function is polynomials in entries of the matrices. So when we act on Schur function, we get product of two Schur functions because we have two faces, one face and the other, and monodromies of these faces, which is just what boundary of black vertices, are Z1 and Z2. So it is not again problem, but these are commuting set of operators. With this set of with different mu, it is commuting set of operators. Then, if we twice applied it twice, what if we apply again this operator, we apply it to this product. I did not what this graph. No, it is not this graph. Черт, я его не нарисовал. Ну ладно. The point that it is involution. No, sorry, not sorry. It is actually, this property is related to the certain sort of dualities for bipartite graphs. I will not explain. But the product, also, sorry, the square of these operators, actually not only square, we can take with a product with different mu, gives, from this, we obtain back this. So this is eigenvalue. So we have these commuting operators and we have this eigenvalue problem with this, no, square of this, here minus, sorry.
Саша, я прошу прощения, мы почти исчерпали время.
Да. Вот next,
если возможно, резюмировать.
Yeah, вот, ну, next example with torus, we have two black vertices and one, and we have similar property. The product of such operators, what these are construct of these black monodromies, this and this. It is in the middle of cycles, A and B cycles. This and sure function is eigenfunction of this product is eigenfunction for this operator. Okay. Some maybe not. No, just short resume. Just actually, what I considered a set of examples. One example was this. It is a relatively simple generalization of Mironov-Morozov-Natanzon and join equation, and it is also have a meaning in Hurwitz number. With the help of graphs, underlying graphs. Here the underlying graph is just a star graph. One white vertex with this product and black vertices on the end of rays from this star. You see, and here in this problem, we can consider any set of partitions mu unrelated to the weight of lambda, because we have here a procedure of completing of cycles I didn't mention. Then next generalization, just as it was examples, the same graph, but what we have some freedom of these matrices, which was related to, if you remember, to solid arrows, and we have this eigenvalue problem, more complicated. It is not Calogero. In no sense, it is not Calogero Hamiltonians because of this. And it is not, you see, this is a set of universal algebra, actually. It is commuting with everything. So this operator, each of these operators commute with all these operators. So this is compatible with this. And we have this eigen. So next example was this. Ну вот я рисовал графы и объяснял, как вот.
Yes.
И вот это вот с тором связано вот это. И все вот эти вот операторы, они коммутируют между собой и коммутируют вот с этим. Между собой, имею в виду, вот при разных мю и лямбда. Но вот эти и эти, они не коммутируют. И эти. То есть эти, вообще говоря, они коммутируют с этим, но они действуют на собственное значение. Они как бы гоняют нас по пространству собственных значений. Просто у этого оператора есть и другие собственные значения. Например, просто произведение функции Шура в каждой из матриц тоже будет собственное значение. Это очевидно. Просто будет произведение того, что было у Mironov-Morozov-Natanzona. Вот. Но то есть там много решений. То есть можно будет разбивать на самые разные группы вот эти вот произведения. И все это, и вот эти операторы, они будут нас гонять по пространству решения вот этого уравнения. Но это будут, excuse my Russian. So we have just what I said about. We have a set of examples, and we have much more examples how to construct commuting operators and eigenvalue problems for them.
Alexander, excuse me. I have a question. You mentioned Guldon-Jackson at some point.
Sorry, repeat, please.
You mentioned the Guldon-Jackson equation.
Cut and join equation. Yes?
No, KP equation.
KP.
KP equation. Yes, I mentioned KP equation. The point that this operator may be rewritten in other variables, but it is a hard task. If we have a matrix, would consider just one matrix Z. No, for k equal 1. This equation for k equal 1. If consider power Newton sums of eigenvalues of this matrix Z. Newton sums. And if you said that these Newton sums are high times of KP equation,
what?
Then this high times what?
High times. You mean
high times?
Long time, asymptotically. What do you mean high time? Long times. Time goes to infinity.
If we have n by n matrix, we have n independent Newton sums.
Yes.
And this say 3 first will be, for example, 3 first, and this 3 first will be may be treated as high times of Guldon-Jackson equation. But
high times. What is high time?
Sasha means the other times of the hierarchy.
No, very roughly, it is better to explain with Korteweg-de Vries equation. We know we have Korteweg-de Vries have many conservation laws. We may consider as Hamiltonians, and we have Hamiltonians commuting Hamiltonian flows, and these times of these flows are called higher Korteweg-de Vries times. And we have the same, but without this good interpretation, the same picture. No, maybe with the same interpretation, but this should be explained. For Guldon-Jackson equation, for Guldon-Jackson, what these high times of Guldon-Jackson equation, what these operators may be rewritten in terms of derivatives and in terms of high times and derivative with respect to high times. It is a not easy task. It was made, actually, it was a starting point of Mironov-Morozov-Natanzon study. And later they transformed it to this matrix form. No, they didn't consider this equation, but with k equal 1, they considered with k equal 1. What is this? For example, cut and join equation itself, it is what if we consider just cut and join equation of Guldon-Jackson, then this will be operator from the so-called of symmetries. There are infinite number of symmetries for Guldon-Jackson equation, which are sometimes they call W in 1 plus infinity symmetries. Actually, we considered it many years ago. And it will be certain generator of this symmetry. Just a symmetry. What does it mean, symmetry? If we act by this operator on so-called tau function of Kp, we'll get new function which will be again tau function of Kp. So I mean,
Okay.
no, you understand. It is a symmetry of tau functions.
Sasha, could you just repeat which operators commute in this picture?
Can what? Which? Repeat,
What
please.
what operators commute?
What these operators commute?
For different
Themselves.
partitions?
Yeah, for arbitrary partitions and between themselves. And all these commute with this.
Mhm.
This also with different partitions commute. Well, this commute with different partitions. And this commute with different partitions. And
But
here
not
we have
not between these families.
Yeah, not between this group and this group.
Okay.
But it is act on all, but all commute with this, and it act on the space of solutions of this eigenproblem. But it is what is written. It is written for special graph, star graph. We can write another graph with another white vertices and with another will be a product of sure function of groups of these matrices. And these operators, how to say, они гоняют нас по пространству решений вот этого, вот this generalized Calogero.
Are there any other questions? Sasha, if not, I'd like to thank you for this interesting talk.
And thank you for I'm sorry for
It's okay. Thank you all. Bye.
Goodbye. Thank you.